So, let's see. After you adjust the radiation, you have to be able to measure it, right? So we're going to scan you in the general area where we think it should be, and then we can generate a scan. Normally, in the old days, these were done with photographic plates. Today, they're all done by computers, right? It's all generated by a computer, and it produces a nice, pretty image with colors and stuff, right? In the old days, it looked just like an X-ray would. And that's what this is, once again, the thyroid. Now, positrons is a relatively new technique called PET scanning, right? We're not talking about scanning your dog or your cat or your goat, right? That's not what we're doing. This is positron emission tomography. And what it does, it makes use of a positron emitter, but the positrons aren't the ones that are being detected because positrons are so reactive, they combine with the electrons and they produce gamma rays. So if positron's emitted, it reacts with some tissue next to it, and then it produces gamma rays. We can measure the gamma rays, and then we can do a blood scan to check for things like brain function and blood flow. These positron emission tomography machines are not very common yet, and they're extremely expensive. I think there's only a few of them in the state, actually. And here's one of the things you can do with it. Here is a normal brain and an Alzheimer's brain. See any difference between the two? Not just barely. I think there's more than just barely. There's a lot less red on here, isn't there? If you look at, well, I don't know, I need a different color. Like, look at this region here, right? And then look at this whole area in here. Look at how much red there is here and how little there is here, right? So this brain is much more active than this brain is in these regions, okay? Computed tomography is a scan of organs that uses X-ray beams, and it uses lots of them. And so it puts a beam through some part of you, and then on the other side it has a detector, and it does so many of them it can actually generate a 3D picture. And on this one you can actually see this part, well, different color I guess, this part right here, right? It's a brain tumor in there, okay? So it doesn't take an expert to tell it that's probably not supposed to be there, right? And it works on tissue density. Now something is not a nuclear, it's not a radiation technique, but it is nuclear in the fact that what it does is magnetic resonance imaging has been around now for quite a while. Well, quite a while. When I was a kid, they didn't have it. I hurt my knee playing football when I was like 10. They take an x-ray and they go, oh, well, there's nothing wrong with your knee. Today, they would have done an MRI on it. Because I know what I did. I destroyed a ligament and some cartilage in it. Okay? Today, I would have had an MRI and they would have fixed it. Back in the 70s, give him some aspirin, send him home. Right? That's it, right? Take 2 aspirin, call me in the morning. That's what they used to do. Okay? What magnetic resonance imaging does is it takes a big magnet and it causes the hydrogen atoms to vibrate. And when these hydrogen atoms are vibrating, they have a sensor that they can tell how much they're vibrating, basically, and they can convert that into an image of your body. Anybody here had an MRI done before? It works really well on soft tissue, right? So like cartilage and ligaments, tendons, things like that. You can see soft tissue damage.
I hated the bear and drink stuff.
The what?
The drinks that they give you before they do the MRI.
That's not an MRI.
I know, I said before they give you the MRI, they have to give you the drink.
No, there's no drink for an MRI.
Barium swallows just.
Barium swallows for something different.
Is the X-ray.
Yeah, that's an X-ray, where they actually look at the barium sulfate that precipitates in your gut. An MRI used to be, it was a big tube, they put you in there, it was this big magnet, and it made a lot of noise, but you don't have to drink anything for it. They do contrast MRI, where they inject you with a dye.
And CT scans, contrast and CT.
Yeah, they do them for CTs as well, right? But yeah, you don't actually drink.
CAT scan.
Yeah, you drank some dye or something. They might have drank it instead of, normally they would inject it into your vein. Yeah. Because that creates more contrast, because the colors, the hydrogen ions in that compound vibrate differently than hydrogen atoms that are in different other molecules. You can actually calculate which molecules you have based upon the vibration of the hydrogens. And this is an MRI of somebody's heart and lungs. All you can see really is an empty space for the lungs, right? Because they are mostly empty space, or mostly air. And here's what the heart looks like in their MRI. I've had MRIs on my knees and my back and everything. It's really good for looking at cartilage. So, which ones of these would be useful for using in the medical world? Would you use this one for medical imaging? Probably not, because it's such a long half-life. But these two, yeah, you could probably use these two, right? 12 hours and 8 hours for half-life. All right, last section. We're going to talk about how to build a nuclear bomb. It's important stuff, right? No? You don't want to know how to build a nuclear bomb? First thing you have to do is you have to get you some uranium-235. That's actually the easier one to come by.
Where do you get that at?
At the uranium store. Actually, there are certain minerals and stuff you can go out and you can collect the uranium from and you can purify it.
Really? How long does that take?
Oh, wow. And a really big centrifuge.
Right. You gotta have that.
How much is that?
Well, the arm on the centrifuge is like, I think the only pictures I've seen was ones that they were trying to build a RAM. The arm on the centrifuge, like everybody knows what a centrifuge is in a lab, spins around. Mm-hmm. The arms on this thing were like 12, like this big around, and it was, I want to say, it was like 50 feet long. Mm. And so the centrifugal force when it spins is enormous because you're trying to separate the 235 from the 236 and 238 and everything else in there. That's the easy part, actually. The hard part is building the trigger. Because to build the trigger mechanism, you need plutonium. And plutonium is really difficult to get.
That's another
You can't just
a Russian.
Yeah, you got to know a Russian that can sell you some plutonium.
There we go.
Yeah. So don't try to build your own bomb. But how does a bomb really work? What is the idea here? And nuclear reactors, like at Sharon Harris, work on the same principle. They work, it's just a controlled bomb, really. Here we have some uranium-235, one neutron. So a neutron hits this uranium atom, causes this uranium atom to become unstable. This uranium atom splits apart into a krypton atom and a barium atom, and it releases 3 more neutrons. So what do you think happens when it releases these 3 neutrons? What do you think these 3 neutrons do? They hit 3 more uranium atoms. And then they split apart, and each one of them releases 3 more, right? Well, in a nuclear reactor, like at Sharon Harris, they put lead rods in there to capture a lot of these neutrons and prevent it from doing a runaway reaction, right? In a nuclear bomb, you just let this happen, releases lots of energy, and it actually accelerates. It looks like this. One more. This is called a chain reaction, right? So here's the first time, the next time, and the next time. Each time you get 3 neutrons released, and so it accelerates. The idea of the plutonium is it provides an initial big burst of neutrons to start the reaction, so it starts bigger. And so you start with a big reaction at the beginning, and then it just grows from there. So yeah, but y'all didn't learn that from me, okay? So don't be trying to buy these things. Seriously, it's like a federal crime to try to buy it. You can go to jail. Yeah. So this is called a chain reaction, one that actually accelerates like this and feeds on itself. The more it happens, the faster the reaction goes. And then just control it at Sharon Harris. What are they actually doing at Sharon Harris? They're doing this reaction, And each time an atom splits apart, it not only releases two new atoms, it releases lots of energy. And what do they do with that energy?
Like electricity.
How do they do that?
Very carefully.
What do you see coming out of the top of Sharon Harris?
Smoke.
It's not smoke, it is steam.
Steam.
They have a giant coffee pot up there. It's really what they're doing, they're boiling water. When this reaction occurs, it releases heat. Capture that heat, turn it into steam, turns a turbine, makes electricity. The chemistry behind it is pretty simple. Actually, the mechanics behind it is very easy. The dangerous part is controlling this
Just take water
reaction.
and a turbine and it will create electricity.
Yeah, if you heat the water up, create steam, it turns.
Heated, does it?
Yeah, it has to be moving, or it has to be heated.
moving.
So like water, like
Make
flowing
it
down the
spin fast
river.
enough.
Yeah, just like a water wheel on a river.
Right.
That just turns a turbine. Same principle, is that when you heat the water up, you create steam, and that turns the turbine, right? And then why is it on a lake? Because they put the hot water back into the lake. The water never touches this, it's just a heat transfer thing, right? Okay. But it's basically a nuclear bomb that's encapsulated, and they're controlling how much of the reaction occurs by the lead rods that they put into the reactor that capture these neutrons in there. Okay? Now, that is nuclear fission, right? So this is fission. What's fission mean? It means to split things apart. Nail. Okay? Fission is if you've taken biology and learned about amoebas, right? They reproduce by fission, don't they? They split apart into two. But what's the opposite of fission?
Fusion.
Is fusion, bringing things together. This is the holy grail of chemistry probably right now. If we could control a fusion reaction on Earth, we would have unlimited power, because this is how the sun operates. Two hydrogen atoms come together, smash into each other, make a helium atom. And does the sun release a lot of energy when it does this?
Oh, yeah.
Yep. If you could do this on Earth and control it, you would have unlimited amounts of energy. We've done it, but it takes us more energy to make it happen than we get back. So it's not very effective right now. Eventually, we'll probably be able to do this. Probably not in our lifetime, but one day, right? What could you do with unlimited energy? Whatever you wanted. There would be no more poverty, basically. Because you could make food, you could make energy, you could build whatever you wanted, you could space travel, because energy wouldn't be a problem anymore. Right? Remember on Back to the Future, they had Mr. Fusion on the car, and he put like a banana peel in there, and that's what they ran on? You'd be good to go. Right? We don't have this yet. This is the Holy Grail. This is the thing, right? So. And that's it for chapter 5.